Okay, so what we're going to talk about today are solutions. We'll talk about concentrations and solution stoichiometry, and then we'll actually migrate over to types of aqueous solutions, talk about solubility, and then the reactions typically that we find in aqueous solutions. So first of all, solutions, what are they? Solutions, this is another name for homogeneous mixture. Okay, so whenever we refer to a solution, we are talking about a homogeneous mixture. What are some of the requirements? So one, as you know, mixtures are variable composition. And those substances that make up your mixture, we call components. Mixtures should be uniform. Okay, in nature. Okay, so in other words, we don't have, if you look, you're not going to have no separation through phase boundaries. Okay, so if this is a homogeneous mixture, then if this is one of my components, it's going to be uniformly distributed throughout, so that if I sample in the upper left corner, it would have the same composition as in the lower right corner. So it's uniform in nature, and mixtures tend to have variable composition. So you can have two solutions. One has fewer components than the other, but they're still made of the same components. And so they're the same type of solution. Solutions can come in different physical states. So we're not restricted to just liquids. You can have a solid solution or a homogeneous mixture. An example would be an alloy, like stainless steel. Okay. You could also have solutions that are in the liquid state. Okay. That would be like an aqueous solution, like salt water. And you can have solutions that are in the gas state. And that an example of that would be like air. Okay. What we're going to focus on are what we call aqueous solutions. So aqueous solutions, they take on the liquid state, and our solvent is water. Okay, and when we do this, don't forget, when something is in an aqueous solution, the abbreviation is AQ. Okay, so let's go through what's a solvent and what's solute. So in a solution, a solute is the minor component. And in a mixture, you can have more than one component. The solvent is the major component. Okay. So for example, we're looking at a saltwater solution, the sodium chloride. This is a minor component. The sodium chloride is a minor component. So sodium chloride is my solute. Since it says AQ, aqueous, my solvent is water. Okay, so those are my aqueous solutions. Now, when we talk about aqueous solutions or liquid solutions in particular, okay, then there are a few other aspects that we need to bear in mind. That is, our solutions are transparent. They can be colored or colorless, but you can see through them. Okay. Another aspect of a true aqueous solution, okay, is that our solutes are dissolved to the ionic or molecular level. So when this happens, we no longer see it. So if you take your, let's say, a tablespoon of sugar and you dissolve it in water, this sugar disappears. But it doesn't really. What happens is it's been dissolved and distributed amongst my solvent molecules, the water, to the point that it's on the molecular level. And so we can't see it because our eyes are not that good in order for us to see the molecules floating around. And finally, when we talk about true solutions, the solute will not settle out over time. Okay, sometimes it looks like you have a solution, like if you have some of the teas, what'll happen is over time, if you let it sit down, you'll see that some material settles down to the bottom. So it's not a true solution. Our solutes will not settle out over time. And typical of all mixtures, you can separate out the components solely through physical means. So we don't need to run a chemical reaction at all. Okay, so now that we know more about solutions, and in particular what we're going to be studying, the aqueous solution, what we do need to know is how do we describe them? And the way we can describe them is like this. I can have a dilute solution, or I can have a concentrated solution. Well, that's great. So what does it mean with a dilute solution? A dilute solution means it has relatively little solute present. And what does concentrated mean? They have relatively large amounts of solute present in solution. The problem with these two descriptions are they're qualitative, and they can be very useful. It's not like we don't use those terms, but if we're trying to run an experiment and have everyone be able to reproduce it, and to have numbers and quantizations that can be relied upon, then we can't use a qualitative description of our solutions and then run a reaction and expect the outcomes to be the same. We need something quantitative so we know exactly what we're talking about. There are many ways to describe, actually, solutions. and their concentrations, but we're going to focus on this one in particular right now. And we will, at a later date, when we do more discussion on solutions, go into the other ways that we can describe the concentration of a solution in greater detail. And the one that we're going to focus on right now is molarity. Okay. And we abbreviate it capital M. But just so you know, when you are doing your calculations with molarity, it can also be useful to remember you can replace this capital M with moles over liters. And that allows us to make sure we can like cancel out our units so we know exactly what we're talking about. And since you know this, then you know the equation for molarity then is the moles of solute divided by the volume, which is the liters. Let me just make that a little prettier here. There we go. The volume, okay, in liters of your solution. So now we can play around with this equation and memorize this. This is super, super important. And that is, not only can we get concentration in molarity, but if we multiply the concentration times volume, you can get the moles of solute. You can get the volume of your solution needed to give you a certain number of moles of solute if we know the moles that we want, and the concentration of the solution. So these two equations are just rewriting this one, but be very facile in your ability to use any of these three versions. So let's do a couple of examples. And when we do these examples, let me go through and tell you, if you're in lab, how you want to make sure you make these solutions. When you make your solution, oftentimes we use what we call a volumetric flask. So for instance, in this case, this is rated to be 1.000 liters, okay? And that's it. You just have your flask and one line. Now, when you want to make your solution, the first thing you're going to add is your solute first. It goes to the bottom. And then then add your solvent. And don't add it all at once. You add a little bit of solvent, swirl it, make sure your solute's dissolving, add a little bit more solvent, okay, swirl it, make sure it's dissolving. So you keep repeating this until you get to the point where you're in the neck, and then you want the bottom of your meniscus at this line. If it's anywhere else, you do not know what the volume of your solution is. So why do we add the solute first? We add the solute first because if you fill your volumetric flask with solvent only, and then you add your solute, there will be an increase in volume so that your total volume will be above that line, and you won't know the concentration nor the volume of your solution. So you have to go solute first, then add your solvent, not the other way around. Okay, so now you know how to make the solution. This is the solution you're going to make. So how many grams of sodium nitrate are needed to make a 0.50 molar. Let's say we want to make 500 milliliters of a 0.50 molar sodium nitrate solution. Okay, so we're going to use our equation. Molarity is equal to moles of solute over volume of solution. That's in liters. Okay. And what are we looking for? We are looking for grams of sodium nitrate. So we need the mass of the solute. But we know how to go from moles to mass. We use molar mass. So now we know this, then we have to rework this equation so that we're getting moles of solute. So M times V, remember that's in liters, is equal to moles of solute. That's going to be step one. And then we go from moles of solute to mass of solute. Okay, so let's go ahead and organize our information from the problem before we do any calculations. So are we given concentration? Yes. Our concentration is 0.50 molar. Okay, so that's good. We have this. What about the volume? It's 500 milliliters. So we need to convert that to liters. And if we move our decimal point, because we're divided by 1,000, it's 0.500 liters. So now we have this. So we can do 1 to get the moles of solute. So that's good. What about step 2? We need the molar mass. So the molar mass, and what sodium nitrate look like? NaNO3. Okay. So let's find out what it is. It's 22.99 for the sodium, plus 14.01 for the nitrogen, plus 48 for 3 oxygens, and you get 85.00 grams per mole. Okay, so now we can actually do the problem. So let's do step 1, followed by step 2. So if we do step 1, we have the moles of solute is going to be equal to the concentration. And in this case, notice I'm going to convert this to moles over liter. Okay. So this is moles over liter. Now, why is this? Because remember, we want to be able to cancel out our units and make sure we're on the right track. So 50 molar sodium nitrate solution can be written this way. And the volume we converted is 0.500 liters. So this is why, because now we canceled out our liters and we end up with units of moles of sodium nitrate. And when we multiply this out, we get 0.025, 2 significant figures. So that's good. That's 3. So we'll end up with an answer of 2 moles of sodium nitrate. So we finished 1. Now we need our molar mass to get the mass of our solute. So for step 2, we take our 0.025 moles of sodium nitrate. We're going to multiply it by our molar mass. It's 85.00 0.00 grams for every 1 mole. Our moles cancel out. And what we end up with is 2.1 grams of sodium nitrate. And this is 2 significant figures. So that's why our answer is in 2 significant figures. Okay, let's do one more. How about what volume of a, let's say 1.56 molar calcium chloride solution is needed to give 6.83 times 10 to the minus 2 moles calcium chloride. Okay, so here, again, molarity is moles of solute over liters of solution. So in this case, now we're looking for the volume in liters of solution. So the volume in liters is going to be the moles of solute divided by our concentration in molarity. So do we have moles of solute? Yes, right here. Do we have concentration? Yes, right here. So we can just plug in our numbers. So the volume in liters is going to be equal to 6.83 times 10 to the minus 2 moles. And now remember that capital M can be moles per liter. So I'm going to say divided by 1.56. I say moles per liter. So now that you know this, 1 over liters is liters, we can cancel that out and get the units we want. So that means that it's not perfect, but it means that we're on the right track for our setup for this problem. Okay, so 6.83 times 10 to the minus 2 divided by 1.56 gives us 0.0438 liters. Okay, I didn't specify the units for the volume, so you can leave it like this, or you could say that's equal to 43.8 milliliters. So that's how we can use concentration in moles to give us the liters of solution. Okay, so let's go ahead and do one more problem. Let's do this one. What is the concentration of let's say 750 milliliters of solution when let's say 25.3 grams of, let's say, gold 3 cyanide is dissolved in water. Okay, and in this case, it's almost a direct usage of our equation. So let's take a look at our equation. So we know that molarity is equal to moles of solute over the volume of the solution, that's in liters. So we are not given moles of solute, but we know first one, we can go from mass to moles using molar mass. And 2, we're going to need to convert milliliters to liters, and then we can use our equation. So let's do number 2 first. So for number 2, the conversion, we know it's 1,000 milliliters in 1 liter. So 0.750 liters of solution at the end. And then let's go ahead and do our molar mass. Okay, so we can actually convert mass to moles. So the molar mass of gold is what? 190, hold on a second. 196.97 plus, for the carbons, I have 3 of them. So 3 times 12.01, and 3 nitrogens, 3 times 14.01. So what we get for our molar mass, 196.97 plus 36.03 plus 42.03. So we get something like 275.03 grams per mole. So now we can convert our mass to moles. Okay, so let's do that. 25.3 grams of gold 3 cyanide. Use our molar mass. We know we're going to divide by the 275.03 grams, multiply it by 1 mole. And what we get is 25.3 divided by 275.03, get 0.09199 moles. Okay, now the reason I double underlined the 9 is just so you know, it should be 3 sig figs because of here, but I'm not done with my calculations because I still need to use my equation. So now let's put in our numbers in the equation. We know the moles of solute, 0.09199 moles of my gold 3 cyanide. And the volume in liters of my solution after I've added enough water, you said we wanted to make 750 milliliters of the solution. It's 0.750 liters. Okay, so that gives us a 0. This is 3 sig figs. That's 3 sig figs. 1, 2, 3 molar gold 3 cyanide solution. So we have done 3 examples. 1, just calculating our concentration. 1, determining the moles of solute, then getting the mass of solute. And the 3rd was getting the volume of a solution if you know moles and you know your concentration. Okay, so we'll take us a break here and then move on to solution dilution.